Question 2. The chemical properties of oxides are related to the chemical bonding present in these compounds. Part A period 3 oxide produces a solution with a pH greater than 10 when it is added to water. So if it is greater than 10, that means we can have what we call a strong, this one is going to be a strong alkali, okay, a strong base that we are going to have here. Remember, a base, an alkali is a soluble base. So this base, you put it in water, you dissolve it, and then you get a hydroxide. So, and of course, this one has to be, if it's a period 3, it has to be for metals. Metals, they are the ones which have basic oxides. Then you dissolve them in water, and then you get a hydroxide. But then for nonmetals, the oxides of nonmetals are acidic. When you dissolve them in water, you form acids, right? So we have to choose from the metals: sodium, magnesium, aluminium. See that? State the formula of the oxide. Since the pH is greater than 10, that is for the bigger one. Okay, it is for the strong oxide. Then I have to choose this one of sodium. Okay, so meaning my answer here is going to be, and they said state the formula. So if you write the name, it becomes wrong. Okay, so always follow instructions. When they say the formula, let it be the formula. So it has to be sodium, then you put a 2 here, and then the oxygen there. Then part B, phosphorus pentaoxide. Remember, this one exists as a dimer, so we don't use P2 or 5. We instead use this one here. Okay, then you're saying phosphorus pentaoxide is added to an excess of sodium hydroxide. Write an equation for the reaction. You see, this one is an acidic oxide. It is an oxide of the nonmetal, so it can react with the base. So we can have P4, then O10 plus. Now here they are saying write an equation for the reaction. Do not put state symbols. They have not put it anywhere, so don't commit yourself. It is only so important when they haven't talked about the state symbols when it comes to energetics. Okay, like what we looked at in question 1 for first ionization energy of sulfur. So plus, we have the sodium hydroxide. Then here you will get sodium phosphate, because when you dissolve this one in water, you will get phosphoric acid. A phosphoric acid gives us a phosphate. You see that? So we shall have sodium phosphate, and the phosphate, it has a 4 here, then we have a -3 here. And you know, for sodium, it is just 1 plus. So we need 3 of the pluses here to balance the 3 minus, right? So meaning I'll have a 3 here, then PO4, and then of course plus water. It has to be water because this is a reaction between the base, an acid, and then water, right? Now we need to balance this one here. I can put a 4 here because there's 4 phosphorus here. So here, when I put the 4, I will balance that, right? And then what will be sodium? Sodium is 4 times 3, that is 12. So I'll put 12 here. You see that? And then hydrogen is going to be 12 here. So meaning if I put 6 here, hydrogen will be 12. Then how about oxygen? Is it balanced? This is 6, then plus the 16, that will be 22. Not so? 22. So here we have 12 for oxygen, and then plus the 10, that will be 22. So balanced, it will be like that. Then part C, table 2.1 shows the melting points of some oxides. Identify the oxide from table 2.1 that contains the element with the highest oxidation number. Okay, let's look at the oxidation numbers here. The one for sulfur dioxide, we are going to have N, okay, then plus the oxidation state of oxygen, of course, is always -2, but there are 2 of them, but then this one has no charge, so we equate to 0. So meaning N here is going to be equal to the plus 4. Okay, plus 4. Then we come to this one. Of course, they said contains the element with the highest oxidation number. So here for hydrogen, of course, we have plus 1, and then oxygen is minus 2. Um, so here I'm putting plus 4 and then the minus 2. Okay, plus 4 is for sulfur, then minus 2 is for oxygen. And then how about for this one? Here is the same thing, N plus, then we shall have 2. Actually, oxygens are 3 times negative 2 is equal to 0. So this one, N will be plus 6, right? So we shall have a plus 6 here, then oxygen is a minus 2. Then silicon, of course, silicon is a plus 4, and oxygen is a minus 2. Sodium is a plus 1, oxygen is a minus 2. Magnesium is a plus 2, oxygen is a minus 2. Aluminium is a plus 3, oxygen is a minus 2. So the highest is this one here, the highest oxidation state. So, and they're saying identify the oxide, so that is sulfur trioxide. Okay, then next, a student suggests the following hypothesis. The melting point of an ionically bonded oxide, ionically meaning the bonding there is ionic, so therefore it is between a metal and a non-metal. So the melting point of an ionically bonded oxide is only determined by the charge on the cation. Now, this one simply implies that the higher the charge on the cation, the higher the melting point. Not so. But then when I come here, the charge here on aluminium is plus 3. You see that? But this is 2072. The charge here for magnesium is a plus 2. Okay? But then here we have 2852. So that means the hypothesis fails, because this one has the oxidation state of magnesium here is less than the oxidation state of what? Aluminium. And yet its melting point is bigger than that of aluminium. You see that? So the hypothesis has to therefore fail. So they said use the table 2.1 to deduce if this hypothesis is true or false, or if there is not enough information to make a conclusion. Explain your answer. So I would say false. Why? Because the melting point of aluminium oxide is less than that of magnesium oxide, yet the oxidation state of aluminium in aluminium oxide is greater than that of magnesium in magnesium what? Oxide. See? So that is that. In fact, let me take this one here. So instead of magnesium oxide, I'm trying to rearrange this such that everything fits on the what? On the two lines. So like that. Part D, state why zinc oxide is described as a Bronsted-Lowry base when it is added to sulfuric acid. What is a Bronsted-Lowry base? This is a proton acceptor, not so. So I'll just say zinc oxide accepts a proton, as simple as that. Accepts a proton. Part E, aluminium oxide is a white amphoteric compound. Roman 1, state the formula of the aluminium containing species produced when aluminium oxide reacts with sodium hydroxide. That is what we call sodium aluminate. Mm. When aluminium oxide when aluminium oxide reacts with sodium hydroxide, so we get what we call sodium aluminate. But they said state the what? The formula. So it is sodium, then aluminate. This one has to be, the OHs have to be 4. Just like that. Then Roman 2, state the formula of the aluminium containing salt produced when aluminium oxide reacts with sulfuric acid. So here, when you get aluminium oxide, then plus an acid, now here, since they said it is amphoteric, it is going to act as a base. So you will get the salt, which is aluminium sulfate. Okay, so I'll put this one like that, sulfate, then plus the water. To balance this, what shall we have? We shall put a 3 here because we have 3 sulfates. And then this one will be 6. So hydrogens will have to be 6 here. I'll put a 3. So 3 oxygens, then plus the 12, that will be 15. This is 12, then plus the 3, 15. So it's balanced. Okay, so this one here is the one that I'm going to have up here, aluminium sulfate.